Hi everyone, my name is Pratik Sampat and today I'm going to talk about our work on improving CPU autoscaling by closing semantic gaps between the OS and the cloud. This work is in collaboration with my colleagues from the University of Illinois, Urbana-Champaign. To quickly summarize, cloud computing paradigms such as microservices and functions as a service have dynamic load requirements and require autoscaling to find optimal resource allocations to adapt to these load changes. Existing autoscalers today struggle with this for two fundamental reasons. First, due to a semantic gap between the cloud and OS interfaces. Autoscalers use CPU as a function of host CPUs, such as millicores and vCPUs. However, operating systems expect CPU resources as a time-shared entity in terms of quota runtime within a period. Second, user space autoscalers lack observability into the application's behavior and have to rely on surrogate metrics to estimate that. We introduce Kscaler, an in-kernel CPU autoscaler that bridges the semantic gap between OS and cloud interfaces. It eliminates the need for surrogate metrics by capturing the application behavior from the Linux scheduler. It is simple and lightweight, allowing it to be highly reactive to workload spikes with virtually no warm-up or training time. Overall, Kscaler achieves a 29.9% CPU savings on average compared to its counterpart autoscalers. The public cloud heavily relies on the pay-per-use model for resources. For CPUs, application requests get translated as a function of time. For example, an application limiting to 0.5 vCPUs or 500 millicores from their cloud orchestrator is essentially limiting its utilization for half a CPU worth of runtime on the system. This limit gets translated to be used in the CPU C group in the OS bandwidth controller, quota and period, which finally enforces these limits. The quota limits the maximum amount of CPU time a task group can run, and the period specifies the duration of this quota enforcement. In this case, for every 100 milliseconds, the application is limited to using 50 milliseconds. First, let's talk about how the bandwidth controller in Linux works on a high level. The bandwidth controller is based on the foundation of time sharing. On a multi-core system, there is a global quota and each run queue receives its local quota. Considering a default period of 100 milliseconds, the quota is first allocated to a global pool. The local pool borrows quota from the global pool in increments of 5 milliseconds, which is the size of the scheduler slice. Once the slice expires, it attempts to borrow more from the global pool. This goes on until the global quota is exhausted, post which the application now throttles for the remainder of the period. When a new period begins, this quota replenishes and the same cycle continues. A task group that wishes to limit its runtime can choose its own quota and period configuration. A smaller period means that a task group's quota replenishes faster than a task group with a longer period. By default, this period is set to 100 milliseconds. The CPU.max interface is used to convey these limits. The wait interface allows us to prioritize between multiple control groups. And the stats interface gives us useful information about how many periods it ran for, how long it ran for, throttle information, and much more. Knowing how many CPU resources are needed upfront is hard. It's even harder when the application is dynamic and load patterns can change in an instant. It's not feasible to tune for these by hand. This brings us to tools like autoscalers, which can account and actuate for these changes automatically. Broadly speaking, there are three major components to an autoscaler. First, it collects data by observing application utilization through various metrics from the OS to user space. Then, it collates all this data in an attempt to predict future load and recommend CPU allocations based on that. Lastly, an actuator component interacts with the interfaces of the OS to set the resource limits correctly to intent. The goal of an autoscaler is to reduce slack as much as it can to achieve the best performance per dollar. Moreover, since load spikes can be unpredictable, it should also be able to adapt to them quickly without any loss in performance. Now, let's talk about these components in a little bit more depth to figure out why autoscaling still struggles today. The problem that forms the crux of our research is the semantic mismatch between OS and cloud interfaces. Recalling from earlier, application requests for resources in terms of vCPUs and millicores, but since CPU C groups are time-shared, they must be converted into a quota and a period. This is essentially attempting to convert a one variable request into two variables. Cloud orchestrators tend to keep this period fixed, which is default to 100 milliseconds, and tune for the quota to achieve this time shared ratio. Cloud orchestrators rarely tune the period today as they do not have any visibility into the application's periodicity. But what really happens when these periods are fixed? Let's take an example when the application's periodicity is larger than the set period. In this case, the application runs for 20 milliseconds, it idles for 150 milliseconds, making its periodicity as 170 milliseconds. An orchestrator using the default period sets the allocation to 200 millicores, whereas in reality it needed just 117 millicores owing to its 20 by 170 ratio. This is a case of over-provisioning. In another example, the application's periodicity is 70 milliseconds, which is smaller than the set period of 100 milliseconds. In this case, a stable application can appear as fluctuating, and an autoscaler that does not consider this periodicity can alternate between over and under provisioning of resources. For a 100 millisecond based allocation, for the first period, it may recommend 700 millicores, the second 500 millicores, and the third 600 millicores, where in reality the optimal allocation is just 571 millicores. User space autoscalers do not know how to observe this periodicity, nor how the application truly behaves. Hence, they collect a variety of surrogate data to model an application behavior. These include observing CPU utilization, throttle, congestion, performance awareness, and many more. This data is then collated and used in many statistical models, queuing theory, machine learning, deep learning, reinforcement learning approaches to predict how many CPU resources will really be needed. While surrogate metrics are good identifiers of bottlenecks and that if more or less resources are now required, it is however difficult to know exactly by how much. Similarly, using complex, more involved prediction techniques lead to requiring higher training and prediction times. Therefore, to protect SLO guarantees, most autoscalers use a larger slack. We assert that user space autoscalers are prone to such inherent semantic mismatches. This leads them to using surrogate metrics and complex modeling techniques, which further causes slow reactivity and inaccurate predictions. We introduce Kscaler, an in-kernel CPU autoscaler that eliminates this semantic mismatch between cloud and OS abstractions. It precisely models the application behavior such as periodicity by observing fine-grained behavior in the scheduler and eliminates any guesswork. Due to Kscaler's simplicity and lightweightedness, it can also quickly tune the bandwidth controller limits when the load requirements change. Coming to Kscaler's design. First, let's talk about the overall flow. Kscaler resides in kernel and extends the bandwidth scheduler. From the user space perspective, first, an application interacts with the C group to set the quota period configuration. These limits are then supplied to the bandwidth control loop. The core of Kscaler is a lightweight technique to observe the run yield patterns within the scheduler loop, which can then be collated to model the periodicity and the quota required. These recommendations can then be exported to the newly created cpu.recommend.max interface, or can also be directly applied if you're operating in the autoscaling mode defined in our policy interface. While Kscaler can observe fine-grained scheduler behavior such as every voluntary and involuntary yield, recording and maintaining this information for each context switch is exorbitantly expensive, especially with fragmented time slices. We develop an algorithm to capture this dynamically changing periodicity of a task. The core idea is that we account for runtime until it voluntarily yields. To achieve that, we employ two high-resolution clocks per run queue. The runtime clock maintains the time since the last run slice, and the idle clock maintains the duration of the last idle slice. When the task yields, we check if it has run for longer than what the scheduler slice was. If it is not, then we know it was an involuntary yield. Otherwise, it was a voluntary yield, and this information now must be captured. Consider the example on the slide. At the first yield, it determines that the runtime is almost equal to the scheduler slice. Hence, the runtime clock continues and the idle clock is reset. This continues for the next few periods until it encounters an idle duration, and then it records it as a voluntary yield. Post that, both the clocks are reset and the process is restarted. In this case, the idle clock is 20 milliseconds and the idle time will be idle clock minus the last runtime slice. That is 15 milliseconds. Similarly, for runtime, it will be the runtime clock minus the idle time minus the summation of a yield correction, which is 25 milliseconds. The yield correction is nothing but minor irregularities in run yield caused due to scheduler delays such as context switch. Now, coming to accounting for throttle. Like mentioned previously, a task throttles when it is run out of its quota and has to wait until the next period. To account for this, we measure the time a task was throttled for and use that time as a correction to compensate the additional time gained. This is used even for other involuntary context switches. During an overload, high degrees of throttling can affect the behavior of this application. If more than 50% of the last history periods were throttled, we exponentially over-provision the CPU resources for every period until the application stabilizes. After the application has stabilized, the application can then scale down to its required limits based on the periodicity modeling that we just spoke about. Moving on, tasks can also potentially spawn multiple threads simultaneously on multiple cores, and we must model all the active run queues while collating this data. We collate data from all run queues either when a new run queue is added or at the end of each period. The challenge is that multiple run queues of an application can be in an inactive state only to be brought back to running. Example, on interrupts. Such behavior leads to inaccurate accounting. It misrepresents the actual application behavior and results in under-recommending of CPU resources. To address this, run queues that are added to the active list are treated as immutable for the duration of the current period. While this may lead to overallocation if some run queues that were scheduled out never got rescheduled back in, this overallocation is minimal as those defunct queues are now removed from the active list in the very next period. Coming to recommendations, there are essentially two ways, an in-kernel and a user space. For in-kernel tuning, when the user tunable history buffer is full, Kscaler determines the worst CPU resource utilization. The Kscaler approach is very simple. The 99th percentile runtime is recorded as the quota, and the 99th percentile runtime plus the 99th percentile idle time is the period. Kscaler also exposes observability data to the user space via eBPF and debugfs trace buffers. This can allow a user space version of Kscaler to employ more sophisticated algorithms like hierarchical policies, but with a significantly reduced reactivity rate. Moving on to the evaluation. First, coming to the methodology. We set up a test bed on a Kubernetes orchestrated cluster running the Docker container runtime on a 64-core x86 architecture. We evaluate 4 varied kinds of application to test the efficacy of Kscaler against. First, Sleeping EVZ simulates web page traffic where sleeping variant allows for sleep wake-up patterns to simulate bursty work. Next, web search and media streaming workloads are from the EPFL Cloud Suite. And lastly, a microservices benchmark hotel reservation from Death Star Bench where an individual service container is tuned for. We compare it against 4 autoscalers, which all require a warm-up or a training time. Kscaler, on the contrary, requires no warm-up or training time. Toward the results, we compare normalized application performance and normalized multi-core CPU resource allocation of the evaluated autoscalers. For Sleeping EVZ and media streaming, both of them exhibit high dynamic periodicity, which does not conform to this 100 millisecond default period. It also is seen that when a saturation is observed via throttle and other metrics, reference autoscalers request for more CPUs to maintain this performance. Web search does not present significant workload variations in the configuration we tested. Hence, all autoscalers perform similarly. Hotel reservation exhibits both high periodicity and load spikes that require CPU resources to be scaled. Autothrottle is the best performing baseline reference of the lot and is often able to achieve peak performance due to its throttle counting. However, it lacks precision and overallocates even as much as 44% compared to Kscaler. On average, Kscaler saves 29.9% of CPU resources while preserving the same performance of the best performing reference autoscaler. Moving on to the reactivity study, where a load spike is injected in the middle of the running workload. All the autoscalers have had a warm-up time, barring Kscaler, which does not need one. First, when the workload is spawned initially, Kscaler immediately adapts to the CPU requests to cater to that, while the reference autoscalers take time, including in minutes, to reach this optimal allocation. Next, when a load spike occurs, Kscaler adapts to this by over-allocating by a little initially due to the throttle and then stabilizes its request. It is also able to do so with minimal loss to performance compared to its counterparts. coming to the closing thoughts and open research opportunities. Lastly, when we talk about cloud providers, cloud users are charged based on CPU resources they request. Kscaler's high reactivity may require cloud providers to also increase telemetry frequency to collect and process the CPU utilization data. Moreover, effects of higher reactivity are also open us up to new opportunities for provisioning and load balancing that caters to this new model across distributed systems. Next, systems with high degrees of contention can pose issues with synchronization as run queue accounting is local and they need to be migrated across. A thorough contention study is required to understand and potentially mitigate its effects. Now, coming to custom schedulers. Today, various metrics such as NUMA affinity, CPU idleness, and many more are used to determine scheduling and load balancing decisions. But periodicity is often overlooked since it only caters to the bandwidth controlled workloads. With the emergence of custom scheduling frameworks such as Ghost and Schedext, there is a potential for a new class of schedulers that caters to this model. Lastly, we have shown that deep kernel observability is instrumental to Kscaler's prowess. There exists various kernel level instrumentation in various areas of memory, network, and I/O, where various projects like Daemon, instruction-based profiling, and many others help provide rich kernel data. The potential of using this rich data to improve kernel-based autoscaling and other kind of resources is immense. In conclusion, Kscaler is an in-kernel CPU autoscaling solution that closes the semantic gap between cloud orchestration and OS scheduling layers. It extends in-kernel telemetry to deliver reactive, millisecond scale performance with zero warm-up time. Results show a CPU savings on an average of 29.9% while preserving the same performance. Kscaler is open sourced on our GitHub page. With this, I look forward to any questions. Thank you.